It's going to start to catch up to you guys. Any constant, of course, goes to 0. So you can see, let me say this right now. If I kept taking derivatives, where am I eventually going to get? Of any polynomial function, I can always take enough derivatives so I get to 0. I like it. This guy is written correctly, meaning it's written as a power, so it's not that hard. Now, I always get somebody to tell me there's a 2 up here. That's a little crazy. What should be up here? Yeah, you go down by 1. Here, same idea. Whatever's up there comes down. And then you do 2 minus 3, negative 1/3. What's wrong with part F? Is it written correctly? Can I use the power rule on something written like this? No, it's not written in power form. What's this look like in power form? 9/7, exactly, right? Now, last time I taught calculus, I noticed a lot of students having trouble remembering that shit. Where are roots on most plants? On the top or the bottom? On the bottom, right? I remember the first time I taught it this way, somebody's like, well, actually, sir, some plants, the roots are on top. Just be quiet. So the root goes on the bottom, and the power goes on the top. That's how you rewrite radical into exponential. Right? Obviously, that's a very basic skill, but if you can't do that, you can't do what we're trying to do. Let me just write this like this so we know where we are with this. Still have to take a derivative. Right? All I did was rewrite the function, right? So how do I take this guy's derivative? What happens with the 9/7? Comes down. 9 minus 7 is 2. So that's what's left up there. Kicking the ass in. By the way, this guy right here, this guy, if you graph x to the 2/3, it's going to look like this. You could actually do that on the paper, Jeff. There you go, buddy. So if I graph this, it's going to look like this. Oh, crap and a half. It's going to have that spot right at 0. What happens to the derivative at 0? What happens when you plug a 0 in there? No, it's to a negative power. So when you plug a 0 in, what does this become? Undefined, or infinite. And right here, that would have an infinite slope right at 0. It would have an infinite slope. It just kind of turns. Infinite slope! Just for like a millisecond, and then it keeps going. So that was one of those situations where it's not differentiable, and you can see, is the derivative continuous at 0? No, it's not defined at 0. So the graph has to have something weird happening at that point. It's got an infinite slope. That's weird. All right. Now, this is the kind of problem you would have saw back in 2.7, and it would have taken you all day. But now, how do I get the slope? Well, I just find f prime. What's f prime? How do I rewrite 2 over x? Sorry. Let's just do that right up here. That's not in the right form. It's not in power form. How do I rewrite that in power form? 2x to the negative 1. I like it. So now, derivative of that is nice. What's the derivative of this guy? Yeah, the negative comes down, makes it plus 2x to the negative 2. And now, where do I want to figure out what the slope is? I want to figure out the slope is at 2. So 12 times 8 plus 2 over 2 squared. Are you guys cool? Just plug in a 2 in, and I get 96.5. So that's what the slope is. And then I could just throw it in the old y minus the y piece equals the slope times x minus the x piece, and blah, blah. I don't care about the rest of it. You guys can do it. So that's a lot quicker question now. So you will see this question a lot as we learn more and more and more derivatives. and derivative rules, this question will show up, but it will always be quicker than it ever was. I'm not have to use the whole limit definition anymore. What about this one? How do I do this thing? It probably involves derivative. But why? Where does this happen?
When the slope is equal to 0?
Good. So if I can find the slope and then set it equal to 0, I can find the locations of all these horizontal tangent lines. So what is the slope of this? X cubed goes to 3x squared. 6x squared becomes 12x. 63x just becomes 63. And the 8's a constant, it dies. Poor little dude. Do you see how you could go backwards? If I gave you that and it said, where did this come from? Do you see how you could just put the 3 back up, take 2 from 12 and put it back up so there's 6, put in x on 63. You can't recover the 8 though, can you? There's no way to know there was an 8 here because it's just 0. There's just some constant. That's the idea of the shape not being pinned down yet. If I just know f prime, I know the shape, but I don't know where the shit it is. I didn't know there was an 8 there unless somebody tells me, which is what I'll do later this semester. That's not what this problem's all about, sorry. So we took a derivative. Now I want to set that derivative equal to 0. Thankfully I can divide by 3, so I don't have to do any weird shit. And then I just have to factor this. And how do you factor that? +21 doesn't have that many factors.
Plus 7
+7
minus 3.
minus 3. So you get x equals -7 and x equals 3. So that's the places where the tangent line would be horizontal. At x equal -7 and x equal 3. Kick ass. Let me see. I want to do one more thing with you guys, unless there's questions on this.
No, I mean, it's just so every time the question would say the tangent line would be horizontal, we just have to set the slope equal to 0.
Yeah,
Okay.
yeah, and that, and like we said earlier, that's such a crucial question. If you were taking 178 instead, which is like 180 light, it's for business majors and so forth. They don't need all the theories. You would focus big time attention on this because in business, you always want to find where the peaks and valleys are. And in fact, in a lot of different places, you want to find where the peaks and valleys are. So you see that question everywhere. You will see it a lot in here too. Just not quite as high of a percentage of the time. Focus. Focus. Okay. All right, so one last little thing. See how much I want to do with this. If I had a function that was actually the product of 2 other functions. So, for example, if I had x squared times, what do you got, Jeff? We don't know anything yet. Oh well, x minus 1 to the 7th, right? And I don't want to, do you want to multiply that out? No, I don't want to multiply that shit out either. There's got to be some way. Each of these individually are simple functions. To be honest, this is something to the 7th, this is something squared. I just don't want to have to put them together and look at the whole thing. There should be some way to look at each piece because each piece is so simple. So if I can make a rule for what to do with this. Now, unfortunately, you can't just take the derivative of each piece. And there's a real quick reason why. If I have x squared, can't I write that as x times x? You can do it, Jeff. Yes, I can. So if I thought the derivative rule here should be the derivative of one of them times the derivative of the other one, is that right? Is the derivative of x squared 1? No. So obviously, the rule for multiplication of 2 functions can't be just multiply the results of each one's derivative. We got to throw that hope out. So, go with me. I'm going to do this. Anytime I do a derivation of a rule, you're not going to have to redo it unless it's a bonus question or something. So here's the derivation of the product rule, and then I'll let you guys out. So how do I find, if I want to know what H prime is, how do I do that every time? Now listen, this is what you guys got to realize. I'm not going to make you do the limit definition for everything now. You're going to have a few to do because we didn't finish 2.8 before, but most of the time you're going to be able to use shortcuts. But when we develop rules, we have to fall back on the definition to prove what the shit's going on. So I've got to come back to this to prove this rule. What is h of x plus h? It's going to be f of x plus h times g of x plus h. Is that cool? All right. And then the rest of it is minus h of x, so minus f of x, g of x. Sweet? Okay. All over h. Now, believe it or not, there is something we can do with this, which is why I wasted my time, or didn't waste my time, writing in sucker. This is nothing you would ever think of on your own necessarily. But this kind of thing happens so often in math that once you see it a few times, you start to go, let me try that every now and again. So this is so frippin' cool. Frippin', Jeff, yeah, sure. So what I can do is this. I can subtract and add the same term So what I did, now look, is what I wrote different from what was here? Does it have a different value? Does it mean something different? No, it's like saying, is 5 plus 2 different from 7? You could say, well, yeah, it's got a 5. No, 5 plus 2 is 7. So since I subtracted and added the same thing, these are the same. Right? And you've got to be saying, why? But do you see what's true about the first two terms here? What do they both have? Those first two in this piece right here, what do they? Yeah, they both have a g of x plus h. So let me factor that out. So I got f of x plus h minus f of x over h. So I'm going to factor out of this, I'm going to factor this g of x plus h. Then I've got plus, and then something very similar over there. What do those two have? F of x. I'm going to take out an f of x. And inside I'm going to have something that should hopefully look familiar. Right? What is this? Limit of this. What is the limit of this piece? That is the definition of, to do it, the limit is h goes to 0 of f of s plus h minus f of s plus h is what? That's the rule for what? What is that? Gonna make me cry. How do you find the derivative of f? What do you do? Limit definition. How do you find f prime? If I give you an f, what do you do? What's the limit definition? Somebody hopefully saying it's that, Jeff. All right, so what the hell is the limit of this then? It's f prime. That is what it is, right? What else do you see up there that looks familiar? Let me make my f less freaky. And then, what happens here when h goes to 0? And here's f of x just sitting there being all innocent. And then what's this? So this, to me, kicks so much ass. It's when you have a product of two functions, you don't do the derivative of each at the same time. You let one have a turn, and then let the other one have a turn. That idea that I just said shows up in so many rules of derivatives. Let's check. come back to, let's see if it recaptures what we did earlier. So remember when I had this? And I said I could write it like that. So any rule that I create, but what is the derivative of x squared? 2x. So I better get frickin' 2x, or else I'm going to throw this whole thing out the frickin' window, right? So if I apply this, this is f and this is g, right? So what's this say? This says the rule is take the derivative of the first times the second plus, leave the first one alone, times the derivative of the second one. X plus x is 2x. Yay. So if I make a rule, it better work on things that worked before, or else that rule is not a rule. It sucks. It should go out. And it worked on that one. Yay. So this is huge. So if I have a product of two functions, its derivative is derivative of the first times the second plus the first times the derivative of the second. They each get a turn on the derivative machine, right? Okay, so obviously, next class will focus on that sucker. I just wanted to get that in your brains to show you, if you have a product, you just can't do the product. Here's what you actually have to do. So we're going to develop a rule for quotients. We're going to develop a rule for functions inside of other functions, composite functions. We're going to make rules for all those things, so we don't have to do limit definition. Okay, that's enough. That's plenty.